So I'm making a recording so Christy can post it. So we are taking a look at your review for your exam. So let me get the exam pulled up, or sorry, the review questions. So we're going to have one related rates question on the test. So the one I wanted to take a look at was problem 2, the ladder. This is like a good middle of the road related rates question. Like you've got to understand the way the concept works, but you're not going to get a super crazy situation like that cone. Now, I think question 3 on your exam review is the cone. So, it's still good practice, but just the geometry involved with the cone question is a little too long for the test. So just keep that in mind when you're studying. So looking at problem 2 here. So we have a 12-foot ladder leaning against a wall. So let's draw our picture. So we got the ground. We got our building. We got our ladder. Yay, artwork. All right, so we got told it's a 12-foot ladder. So let's put that in our drawing. It's leaning against a wall. If the top of the ladder slides down the wall at a rate of 2 feet per second. Okay. So this ladder is now sliding down. So I like to put a little double arrow for my direction of movement. And then it's going down at 2 feet per second. How fast is the bottom of the ladder moving along the ground? All right, so if the top of the ladder is sliding down, then the bottom should be going out as the top slides down. So this one is going to go outwards this way. But this is our question mark feet per second. And then they tell us when the bottom of the ladder is 4 feet from the wall. So that 4 feet is our freeze frame on when we're taking a snapshot and looking at this. All right, now, so I do know in Mathland, my building here, my wall, definitely hits the ground at a right angle. And my ladder makes a triangle. So I have a right triangle. And the quantities I'm looking at here are the lengths of the sides of the triangle. So I need a formula that relates the sides of the lengths of the triangle, the lengths of the sides of the triangle. So what theorem does that? Yep, Pythagorean theorem. So I need to label these sides something. I'm going to go with X, Y, and Z because why not? So I'm going to call the horizontal side X. So X is 4 feet. And now this question mark rate, this is dx dt. So this is the thing we're trying to solve for. I'm going to call this vertical side Y. So that means this 2 feet per second, this is dy dt. And then for a third side, we'll call this side Z. So this 12 feet is Z. All right, so I'm going to write my Pythagorean theorem formula. I've got x squared plus y squared equals z squared. Now, I want to differentiate this with respect to time. So we're going to take our derivative of everything, but every time we take a derivative of a term, we're going to have the chain rule come into play, and the chain rule is going to give us our related rates parts. So our derivative of 2x That's our power rule. So the 2 is going to come down. So I'll have 2 times x to the first. And then here's our chain rule showing up, times the derivative of x with respect to time. So I have 2x to the first power times dx dt. And now we're just going to do that 2 more times. So plus the y squared is going to be the same thing, 2y times dy dt equals 2z times dz dt. All right, so I've got a formula that has, I know dy dt, so that's something I get to fill in. I know my x and my z, but I don't know my y value in this snapshot, and I don't know dz dt. So I've got 2 more like, I've got to think about this values. Yep.
The derivative line of the 2x but not the 2y.
It's not a derivative line, it's actually the first power. Yeah. But yeah, fair. It was inconsistent notation, and it did look like a prime. No, you're totally excellent question. Yeah. If you guys got any questions about my handwriting, just interrupt me in the middle of talking, because otherwise you're going to sit here the whole time going, is that a 2 or a 5 or a what? And I'm going to be like, it's an S because my handwriting's bad. I've literally had that question happen in class before. My 5s, 9, and S's all look alike if I write too fast. So yeah, those were ones. But yeah, if it was a prime, that would have been like extra confusing because then I had an X prime and I wrote dx dt. Like, yeah. All right, so I know my X and my Z in my snapshot time frame, but I can use my original Pythagorean theorem formula to solve for the Y. I know the 12 and the 4, so I'm going to plug that in there to get the Y value. So let's sidebar that. So x squared plus y squared equals z squared. X is 4. Y is my unknown. Z is 12. So I have 4 squared plus 12 squared plus y squared equals 12 squared. So we got 16 plus y squared equals 144. And then we minus the 16. So y squared is 128. Now, to get y by itself, we're going to square root both sides. But anytime we square root, we always have to remember we have the potential for a positive or negative number. Now, in the context of this problem, y is a distance. Distances are usually positive numbers. Now, you might have some weird scenarios in physics or whatnot where you put some negatives on there, but in math class, generally, if it's a distance, we keep it positive. So we have the positive square root of 128. Now, WebWork should accept the answer with the positive square root of 128. Technically, that square root does reduce, and some of y'all's calculators might spit out the reduction. 128 is 64 times 2, and then the square root of 64 is 8. So this is the same as 8 square roots of 2. But WebWork doesn't particularly care if you reduce the square roots or not once you're in calculus. It did when you were in pre-cal, but not anymore. All right, so now I've got my x, my y, and my z. I know dy dt. I'm solving for dx dt. So the only thing I don't know is dz dt. So dz dt, I look back at my figure. Well, z is the length of the ladder. Does the ladder ever change length?
No.
Not in the context of this problem. Certainly we could have ladders that change lengths, but in this one, they just said it's a 12-foot ladder. No talk about it changing lengths. So if it never changes, then its rate of change is 0. So now I can fill in something for all of my things except the unknown. Now I can solve this. So in this particular related rates problem, one of our things doesn't change in length, so we had a rate that was 0. That may not be the way it works on the test. The test question might be a little bit different, but that's just the way this one happens to work. So now we're going to fill in what we know. So 2, x is 4, dx dt is our unknown, plus 2, y is that positive 8 square roots of 2, dy dt is 2. Now, the other thing I forgot to consider here is whether our rate would be positive or negative. So when I look at the y side, I wrote the down arrow. So that's decreasing. So we should actually put a negative on our 2 feet per second here. Now, when we look at our dx dt, that's going out. So we are expecting dx dt to be positive. Now, if we don't notice the sign right away and we work through the calculation, at the end, we'd get dx dt is negative. And then we just have to like ask ourselves, does that negative make sense? And then that should lead us to backtrack to putting a negative here. So if you accidentally mix up the sign, it just means the answer you get at the end will be the opposite sign, but the number will actually still work. Now, in other problems, having the wrong sign might actually screw up the calculation. So we do want to be careful of that. Our z was 12, but our dz dt is the lovely 0. So we're going to have 0 on the right side. I've got 8 times dx dt. And then this will be negative 32 square roots of 2. So then we'll add the number over. So 8 times dx dt equals positive 32 square roots of 2. And then we divide by 8. Yep. So we have dx over dt equals 4 square roots of 2. And it's positive because the x distance is getting bigger. And this would be in units, this would be a feet per second. So we can type in 4 square roots of 2 in WebWork, or we could type in what the decimal is, and WebWork should take either answer. Yeah. So first question on the test is going to be related rates. 5, because we're lazy and there's always 5. But some of the problems have like multiple question parts. So the next 2 questions have to do with the first and second derivative tests. But the problem I want to pick out from the review for random reasons, yes, I'm randomly, deliberately choosing problem 9. Does everyone know why I'm being so sus about how I'm saying that? So why do you think I'm being so suspect about why I'm randomly choosing problem 9?
So it'd be similar to the test.
I didn't say that.
I'm just thinking that.
Yeah, I mean, you're just thinking out loud. So if anyone asks, did I tell you what was going to be on the test? No, I just randomly picked problem 9. Random. I'm making this very explicit. If there's anybody on Spectrum who might be missing it, like, yes, this is deliberate. So problem 9 here is the one where we get a picture. So problems 4 through 8 are all a bunch of equations that ask you about the first derivative test. And then problem 9 feels like the odd one out. So it's real easy to be like, oh, it's going to be a function because they gave us 5 freaking questions with functions. And this was the weird one. So let's make sure we do the weird one. So this graph here is the derivative, not the function. That is the first mistake that is easy to make here. So now on WebWork, we can actually zoom in and make the graph bigger. So I did that. So we got a prettier looking graph here. Now, the question is, where is f of x increasing and decreasing? And then there is going to be a follow-up question. Where's the max or the mins? So this is enough information to answer that question. But at least the way I taught first derivative test, I didn't do it from looking at the graph. I did it from a number line. So reading this graph for me, like my brain keeps wanting to read where the maxes and mins on this graph are instead of where the zeros on the graph are. So what I actually do is I take the graph and I turn it back into a number line. So here's my big number line. Now I want to look for where are the zeros on this graph, because where the first derivative equals 0, that's where the critical values on the graph are. So that was like our first step in the first derivative test, was find the critical values. Find where f prime of x equals 0. So this is my graph of the derivative. So I've got a value at -2, -1, and 0, and 1. So they kind of went like super crazy on how many critical numbers we got. Now, the next thing we did, which would be 2, not 3, is we pick some test values. Now, normally we're dealing with a function, so we look at our number line and we're like, all right, I could pick -3, and then I could pick like -1.5, and then -0.5, +0.5, and then I could go with 2. So that's like the numbers I would test if I had the function formula. Now, it turns out this step is actually a little bit nicer with the graph, because I don't actually have to plug in the number and do all the number crunching. I just have to look and see what the graph was doing. So at -3, or I mean, honestly, that looks like -5 because my handwriting is so bad. So at -3, this is some very negative number. So everything before -2, the derivative is negative values here. Now between -2 and -1, now my graph is above the x-axis, so that is some positive number. So now I've got pluses on this part of the graph. Now between -1 and 0, it bounced at the -1, so I've got positives again. Between the 0 and the 1, the graph went below the axis again, so these are negative values. And then after 2, it goes back up. So those are positive values. So the testing step was actually much faster than when we had to do this with a formula. Now I'm going to scoot this down a little bit. Now, what I like to do once I have those pictures drawn in is I like to actually draw like the direction the graph is going. So those negative values mean that our function is decreasing there. So that is a downward trajectory. Like I always think of it as a roller coaster. So this is where we're going downhill on the roller coaster. Then positive values mean an uphill part. So I got 2 uphill parts. Then it goes down again. And then it goes up again. So now that I got my down and my up angled arrows, now if I actually connect the arrows, I can see where the graph is making a minimum or a maximum. So it's going to look a little weird, but when I go from decreasing to increasing, this makes a minimum. when I go from increasing to decreasing, uphill to downhill, this is making a little maximum. And then that last one here is making a little minimum. So I kind of like jumped straight to the end because normally the focus is on finding the maxes and the mins, not stating where it's increasing and decreasing. So we just did that. So I'm going to go ahead and answer that bonus question first. So we've got a minimum at x equals -2 and x equals 1. Because that's where our arrows changed direction, going from downhill to uphill, decreasing to increasing. Now our maximum, our local max, is at x equals 0. That's the point when it changed from increasing to decreasing. All right, now we just got to go back and answer the other two parts. So where is it increasing? So I look from -2 to -1. That's my first stretch that had positive slopes. And then I had from -1 to 0. And then from 1 to infinity. Now, WebWork being the lovely gem that it is inconsistent in how you type in your answers. So on some questions, you would type these 3 things in and you'd put commas in between. This one, though, has the little help intervals thing next to it. So this one actually wants the union symbols in between. Now, this is not capital U. It may take it with capital U, but it is technically a different symbol. It took it with the capital U. Cool. Now I'm going to be really weird. Or if you do a mix, you use the union symbol and you use the capital U, it takes it. It's actually a well-programmed question. What a shock. All right, now our decreasing is just going to be the flip side. So from -infinity to -2. And then from 0 to 1. Now, the answer does need to be written like this. Like, I know it's really tempting to say, isn't that just from -2 to 0? But -1 has parentheses here because at -1 itself, the slope is 0. So at -1, it is neither increasing nor decreasing. Now, both sides of -1, it is increasing, but the graph is like going up, flattening, and then going up again. So at -1 itself, it balances back to 0 before going up again.
Would that make it an inflection point, -1?
More than likely. I can't think of a way to draw the graph without it being an inflection point, but technically we'd want to look at the second derivative and make sure the concavity changes. Mhm.
If this question was on the test, would we need to use, or would we use commas?
Do we say it again?
Like, would we have to use the union sign, or would we use commas?
That would more be a question for Christy, but I can't imagine her taking off points if you put commas instead of the U's. Just in a technical mathematical sense, the U is the correct symbol. All right, so that was our first derivative test. Our second derivative test. Now we could kind of reason through the second derivative from the graph of the first derivative, but it's kind of annoying. And mostly it's annoying because it's actually really hard to estimate where the maxes and mins are. So we're going to look at problem 10. So we've got a lovely little function here. And it's asking, where do the inflection points occur? Where is it concave down? Where is it concave up? And then here, see at the end, it says, note, state the open intervals of concavity as a comma-separated list. Like problem 9 to problem 10 totally changes the way we type. So this is why I don't think Christy will be like, no, you had to put U's because WebWork isn't even consistent. All right, but our points of inflection, our concavity, those all come from our second derivative. So our first step is to take this function and find the second derivative. So here we've got a nice polynomial. We just have to use the power rule again. We don't even have to worry about related rates. We're just doing a straight derivative and then another derivative. So I will have -5 times derivative of x cubed is 3x squared minus 27 times derivative of x squared is 2x to the first plus 24 times the derivative of x to the first becomes 1x to the 0, which is technically just 1. So you could technically just write plus 24. And then minus the derivative of a constant is 0. So if you've done a lot of derivatives the way you should have, if you've been doing your homework and doing extra practice, you may not have to write this step like this. I'm just doing this if you're still not as comfortable with your derivatives. But most people, once they're comfortable enough, will actually just jump straight to -15x squared minus, and you might have to crunch on the calculator, 27 times 2 is 54, x plus 24. Like totally normal to jump straight to there if you're comfortable doing your number crunching and doing your derivatives. But nothing wrong with taking the extra line either. So now that we have our cleaned up derivative, now we can do our second derivative. So that'll be -15 times 2x to the first minus 54. That'll be 1x to the 0, so times 1 plus 24. Derivative of 24, though, is 0. So we have -30x minus 54. That is our second derivative. So second derivative test says find the critical value, set it equal to 0. So I'm going to add the 54 over. And then I'll divide by the -30. Now, WebWork will be perfectly happy to take 54 over -30, but it does technically reduce. And in fact, they're both divisible by 6 because they're even and multiples of 3. So 6 goes into 54 9 times, and 6 goes into 30 5 times. So our x value is -9/5. Now we want to consider what's happening on either side of -9/5 with our second derivative. So -9/5 is -1.8. So I can pick a test value of -2, and then I'll be lazy and I'll pick a test value of 0. So if I plug in 0, -30 times 0 is 0, minus 54, I'm going to get all negatives to the right. Now, if I plug in -2, Negative 30 times negative 2 is positive 60. Minus 54 is going to be positive 6. So everything on the left is going to be positive. Now, I don't like just leaving my number lines with the pluses and minuses because to me, it looks exactly the same as the first derivative. So I always like go back and add the extra step of, all right, second derivative line. So this is my concave up region. My negatives is concave down. So now we can answer the question. The inflection point is at x equals negative 9/5. And then we are concave up from negative infinity to negative 9/5, all with parentheses. And then concave down on the flip side from negative 9/5 to infinity. Now, it might be a little more crunchy on the test, but that's the overall basic idea for our second derivative test. Like you might have to do a little more algebraic work, but like since we're asking you to do two derivatives, we're not going to put any function that's too crazy there because like doing a second derivative of a product rule and then having to set it equal to 0 is too much work for this question. So it may not be a third power, but it's still going to be a polynomial. It might be, though. I don't know. I haven't seen Christie's test. I've just seen our generic test that we're writing from. All right, let's see. Now, when you look at the rest of the problems in the practice problems, the functions are going to be a little ugly that you're doing the second derivative of. Just think of it as good practice with doing the derivative and applying the test, but they are a little inauthentic for what we expect on the test. They're all going to take a little longer than what the test question will. Now, I want to make sure we have time to do the L'Hopital's questions because you guys may not have gotten the chance to like do all of them last time. Because the L'Hopital question is the last one on the test, but it's going to be a kind of choose your own adventure. So we're going to give you a list of 3 limits, but you only have to do 2 of them. So the directions at the top are going to say choose which 2 of these limits you're going to do. But one of them could look like this one here, problem 19. And again, I don't know what Christie's going to put on the test, but this is one of the ones. I'm going to put something kind of similar to this on mine, I know. I mean, I'm randomly selecting this problem. Yes, someone chuckled a little. All right, so we've got the limit as t approaches 0 from the right of 3 over sine of t minus 5 over t. So our first step, as always, is just to plug in the 0 and see what happens. So 3 over sine of 0. Now these are from the right. So as we approach 0 from the right, we're getting a bunch of positive numbers, but the sine of 0 is 0. So 3 over 0 is giving us an infinity. And then 5 over 0 is doing the same thing. I'm plugging in numbers from the positive side of 0. So it's positive, but I'm going to get infinity. So I actually have infinity minus infinity, which is, what do I do with this? I don't know which infinity is bigger. So this could yield infinity. This could yield zero. This could yield negative infinity. This could even yield a constant if things got really weird. But right now, I don't know. And this isn't 0 over 0 or infinity over infinity. So I can't even use L'Hopital straight out the gate. So the first thing we actually have to do is we're going to have to algebra these fractions together. So we're still going to have our limit over and over again. But I have 3 over sine of t. I'm going to leave a little space, then minus 5 over t. So to combine these algebraically, I am combining fractions. What do I need to make fractions smash? Yep. So my denominators are sine of t and t. So my common denominator is both of those things. So my first fraction has sine of t, but it's missing t. So I'm going to multiply by t over t. That's just a weird form of 1. I can always multiply by a weird form of 1. Now my other fraction is missing the sine of t. So that's what I'm going to multiply by. So on top of this fraction, I have 3t minus 5 sine t. And the bottom of the fraction is t times sine of t. So now I've got it in a fraction form. So now it's like, ooh, maybe L'Hopital indeterminate form will work now. So now if I plug in my 0, I'm going to get 0 minus, well, 3 times 0 minus 5 times 0, because sine of 0 is 0, over 0 times sine of 0. So we got our indeterminate form. Now I can use L'Hopital's rule. So I'm going to take the derivative of the top on its own and the derivative of the bottom on its own. I still have my same limit as t approaches 0 from the right. The derivative of 3t is 3 minus 5 times the derivative of sine t is cosine t. Now on the bottom, though, we got a product rule. So we've got a times b. So I usually do this by derivative of the first one. Derivative of t is 1 times, keep the second one the same. So 1 times sine t plus, now I keep my first one, times derivative of the second one is cosine t. And then I always like to double check. So I did derivative of t and then I didn't. I kept sine t and then I did the derivative of it. And they're like mixed matched. So yes, I've done my product rule. And now we plug in the 0 and see what happens. So we have 3 minus 5 times the cosine of 0 divided by the sine of 0 plus 0 times the cosine of 0. So on the bottom, it's like, oh, well, sine of 0 is still 0 plus 0 times that's 0. So I still got 0 on the bottom. But on top, I didn't get 0. Cosine of 0 is 1. So 3 minus 5 times 1 is -2. So now our question is it infinity or is it negative infinity?
Son.
Yep, because the 2 is negative. But on the bottom, we want to make sure and consider like everything is coming from the positive side, and it is because we had the limit from the positive side. So sine from the right is positive values. 0, t from the right is positive, and then cosine of 0 is +1. So this is all 0 from the positive side. So the -2 will make this answer negative infinity. But see, if my numbers were a little bit different, the 3 and the 5, I could have had positive infinity. Or if they were the same, I could have had another L'Hopital situation. It won't do that on the test. Because we don't want to make you do another L'Hopital on something that was a product rule. Once is okay, twice, hell no.
Zero, the left side, would it still be negative?
So if it was from the left side, our sine values would be negative, and then our t values would be negative. So we'd have like -0 side plus -0 side, and then the cosine would still be 1. So those would all be negative zeros, and then divided by, or with -2 on top, then it would have been positive infinity. Just because it's doing one of those split behavior things. Like if we could see the graph, it'd be much more obvious, but figuring it from the numbers, like, yeah. So yeah, that's another way to like change this question, but not really, is just to change the 0 from the left instead of 0 from the right. Different answer. So L'Hopital is a really powerful tool, but you have to be very careful that you only apply it when you have a situation where it applies. It must be 0 over 0 or infinity over infinity for us to use L'Hopital's rule. So at the start, we could not use L'Hopital. Now you've got several other L'Hopital's rules in there, but I want to make sure we hit an optimization problem as well. So I'm going to go back to 14. All right, so they've given us a picture, and in the picture, they've labeled some sides for us. But we've got 800 feet of fencing to make a pen for hogs. And for some weird reason, we've decided using the river as one side is totally fine. So we don't have to lay fence on the river side. So we want to maximize the area of this pen using all of the fencing we can. So our key phrase there is maximize the area. So this means I want an area function. So an area equation in terms of one variable. That was our requirement for doing our derivative and finding a critical value, is we needed it all in terms of one variable. Now, I do know the area of this pen. That is length times width. But that is 2 variables on the right side. But I haven't used my 800 feet of fencing yet. So when I look at my fence here, I've got my width, and then I've got my length showing up twice. So it's not quite the perimeter, but all of my fencing together is 2 L's plus a W. Those numbers, those sides, have to add up to be 800. So now I have another equation that I can make use of. Now here we have the question of, should I solve for W or should I solve for L? And it actually doesn't matter. Both ways will work, but one of them is a little less algebraic ugly. So I'm going to keep W and I'm going to get rid of the 2L. Because if I try to solve for L, I'm going to have to divide by 2. And like certainly we can handle dividing by 2, but this way is going to mean less fractions. So I know W is the same as 800 minus 2L. So I'm going to go put this in place of W. Now, remember, when you are making a substitution, so I'm going to like start my line of work. I've got A equals L times, and then I just write down my 800 minus 2L. And so I see my students like write this on the test. They've made the substitution and they're like perfectly happy with the way this looks. So then they write, all right, that's 800L minus 2L. And then they just get, what, 798L. And then they take the derivative of that. And then they're like, my variable disappeared. That is not supposed to happen. Oh crap, what did I do wrong? So whenever you make a substitution into a formula, any substitution, this is where I'm going to tell a really cheesy math joke. And they should have used it on Dropout and didn't. But whenever you substitute, you use parentheses. So parentheses are the condoms of mathematics. So practice safe math. When you are inserting something, wrap it. That is what is missing in the work here. It is such a horrible joke. You will remember it. Like, I'm substituting. Oh, wrap it. But I promise you, it will save you some heartache too. You don't want your math equation to get pregnant. All right, so now that we've got the parentheses, now we can see, oh, this L actually distributes. So we do have that 800L, but we have minus 2L squared. And that is what is going to make our derivative now work for us. So now optimization, it's all in terms of one variable. I can take the derivative and set it equal to 0. So A prime equals the derivative of 800L will be 800 minus 2 times the derivative of L squared is 2L. And we set this equal to 0. So I've got 800 minus 4L's equals 0. I add the 4L over and then divide by the 4. So my length is 200 feet. Now I want to know what my width is. Whoop. I bring it back over here to my W equation. 800 minus 2 times 200. Gives me a width of 400 feet. And then I believe WebWork actually even asks, what is the maximum area? And that is 200 times 400, which is a whopping 80,000 square feet. Now, WebWork is a little annoying on this question. Because all of our work, I can fill in almost all of what it is asking for. I'm just typing it in real quick so I can give you guys a screenshot of like what it liked and what it didn't like, or more what we didn't actually solve for. So they asked for the area of the pen as a function of its length. That is the formula we got here, 800L minus 2L squared. And then we solved for L. And then they said, all right, now rewind, go back and write the area as a function of its width. Like, we can do that, but we didn't need to do that to solve the rest of the problem. But I can do that by solving for L instead of solving for W with my perimeter formula. I'll have to divide by 2, so I'll get a fraction. And then I'll have to type that in here with the W's instead. And if I did my derivative test, I took the derivative and set that equal to 0 and solved, I would get 400. But I also got my 400 just by back substituting. So it's technically 1 minute past, so I'm not going to do that last little part there, but I did just explain how you would do it. So on the test, Christy is not going to direct you which way to do the problem. In fact, you're going to have to like draw the diagram. Well, depends on how she writes the problem. She might give you the diagram. You might have to draw it yourself. I think the one I'm doing, I'm probably going to draw it. The only reason we draw it is just to like define, like put the variables in the picture for you. Just because if you define the picture a little bit different way, it can kind of mess with your derivative later on. So we might like do that favor for y'all on the test. But that is the whole test, all 5 questions. So 1 related rates, 1 optimization. Those are your 2 word problems. A first derivative test, a second derivative test, and then the choose your own adventure L'Hopital's rule at the end. All right, I'm going to send the recording of this to Christy, and she should be posting it for y'all.
You have a good one?
Y'all too?